We have Caroline Pantofaru. She earned her PhD degree from CMU in 2008, working with Marcel Hébert there. She joined Willow Garage in 2008 as a computer vision research scientist. Her current focus is on perceiving people, from detection to tracking to activity recognition. We also have Radu Rusu. Yes, Radu Rusu. He earned his PhD from the Technische Universität München. My German is horrible. And he joined Willow Garage in 2009 as a research scientist. His current research interests include real-time perception and 3D semantic mapping and object recognition for mobile manipulation platforms. Help me welcome our speakers.
Hi all, thanks for having us here today. So today Radu and I are going to be tag teaming this talk a little bit. We're going to start off by talking about what Willow Garage is, for those of you who don't know. And then I'm going to go over a fairly random but hopefully interesting set of perception projects at Willow Garage. And then I'll pass it off to Radu, who's going to deep dive into the world of perception in ND. So let's start off with what is Willow Garage? Well, Willow Garage is a privately funded personal robotics research and development company in Menlo Park. We have about 60 people working with us right now, with a wide array of specialties, as you can think of a robotics company, from researchers to software engineers to engineers of various sorts to psychologists. And we also have a ton of interns, and I'm going to use this opportunity to do a very, very early intern plug for those professors and students in the room. We have about 20 interns a summer. Our summer this summer is actually full, but we're taking interns for the fall, so please come see us afterwards. Very early plug. So what is personal robotics, and specifically indoor personal robotics that we focus on? Well, we define it as robots that operate in the same environment as people, without using cages or other restrictive devices like industrial robots do. So our main personal robot is the PR2, the personal robot 2 that you see in this image. It's got a base that's about the size of a wheelchair, so it can go anywhere that's ADA compliant, that's American Disabilities Act compliant. It's about 4.5 feet tall and actually stretches to about 5.5 feet tall when its torso lifts. That changes things a lot for me because it's shorter than me and goes to taller than me. And when it's nice and tall, it can reach tabletops and shelves and other such things. It drives around on casters, so it's very stable, and it has 2 arms that are actually counterbalanced, so they feel a lot lighter than they are, which is great when you're operating around people. It's much more appropriate for human environments. Mostly what this robot is for is research and prototyping. It's meant to be a general purpose platform on which you can turn a hardware problem. So robotics, traditionally, if you wanted to start a lab, you had to build a robot first, and that took a really long time. The startup cost to a robotics lab was huge. And what you'd really rather it be, if you're a software person, is someone hands you a robot or you buy a robot, and then you can work on the software problem. Well, before, there really weren't any robot platforms that kind of fit this personal robots paradigm. And the PR2 is meant to fill that void. It's meant to be a robot on which you can prototype and do research. There are right now about 15 PR2s out in the world, and hopefully that number is growing. But hardware is actually only a small part of what we do. Most of us actually work on software and on research. What we want to do is write higher level software, perception algorithms, manipulation algorithms, all that type of stuff. But in order to do that, you need a standardized robot architecture. And for us, that's the Robot Operating System, or ROS, which right now is in its 3rd sort of big release. That's called Diamondback, and Diamondback Turtle, actually, which is what that great picture is for. ROS, at its core, is a message passing system. You have a distributed system of nodes, where different nodes do different kinds of processing for your robot, like camera drivers, or perception algorithms, or controllers, and it lets them pass messages between each other so they can talk in a distributed way. So you can have some of them running on board, some of them running off board, perhaps some of them even running in the cloud. But the most important thing about ROS is that it standardizes data structures and some of the basic processing. So that when we write our higher level software, we can exchange it, work with other people, and in general, build a community that can actually work together. So, oh, and most importantly, I can't forget this, ROS is open source. It's released as BSD. And what that means is that if you build on top of it, you can use your work for whatever you want, including the ROS components that below it, including, if you'd like, to start your own company. Nothing's preventing you from using any of these components. In the same spirit, we have a couple of perception libraries that are also open source. You've probably heard about OpenCV, and I'll give you a bit of an update on that later. And there's also the newer point cloud library, which Radu's going to talk about more in depth. And these are perception building blocks, also open source, that you can use in your code, build upon, and hopefully share your algorithms. And hopefully one day soon, these will merge into an open perception library. But really, robots and software are not actually what we want to do. What we want to do is to build a community of roboticists that are working on this personal robotics problem. If you think about personal robots today, they're kind of the Roomba, and that's about it. And it's because it's really hard to do personal robotics, and no one has expertise to do all of it. So the hope is if we can work together as a community, all doing the open source bits, then we can get to the point where there can be a personal robotics industry. And then we can all have companies, and there'll be plenty of pieces of the pie to share. There'll be plenty to go around at that point. So right now, as you can see on this map, there's actually a ton of places that have ROS repositories that are helping to develop ROS right now, and we hope this number will grow. So to summarize that, Willow Garage's goals are really to create an industry. And we know that in order to do that, we need to share the engineering burden. We know we need to avoid duplicating work. So that's a lot of what our open source policy is about. Share the work, don't duplicate it. We need testing standards. And in general, we need to do better science. So it's not just do demo. You can actually get numerical results and compare algorithms. In order to do that, we need to build a community. So I've been going on about Willow Garage for a little while. Let me bring us back into the world of perception for a bit. And, well, for the rest of the talk. And first of all, talk about sort of why you should care as a computer vision community about robotics right now. So computer vision, especially recently, has been a lot about web imagery. Has been about large data sets of single images from single cameras, all disparate, taken from different cameras at different times, all over the place. Well, you might say that a robot, well, it has cameras. It actually has video cameras. It has a number of them. It has 2 pairs of stereo cameras in what you would consider its head, plus a higher resolution camera. It also has a camera on each forearm so it can see what it's holding in its hand. Well, all these cameras produce video. That's actually really relevant right now because there's a ton of video online now. So even for those who are interested mostly in the online space, video is becoming a huge, huge issue at the moment. Now, okay, so that's not much of a stretch. Computer vision has always looked at video. That's fine. Okay, well, let's look at something else, something that computer vision has kind of considered cheating in recently. Let's look at 3D information. So I told you that a robot has a couple of pairs of stereo cameras on its head. Well, it also has a texture projector that I just highlighted. And what that does is projects texture into the scene to improve your stereo information. This might sound familiar to some of you. It also has a couple of laser rangefinders. One in its base that just does a 2D scan, and that's mainly for obstacle avoidance. And one in, I guess you would call its neck, that tilts, so it gives you a nice 3D perception of the scene. So this kind of 3D data, especially laser range data, it's sort of been considered cheating in the computer vision community. But with the recent introduction of 3D consumer cameras, stereo consumer cameras. And especially with the introduction of the Kinect, this is suddenly extremely relevant for the computer vision community as a whole. There's going to be more and more 3D data online out in the world, and it's time we all deal with it. Finally, a source of data that's really been considered cheating in the computer vision community, and that's situational awareness data. So I've highlighted one of the robot's casters sort of down there below to represent the robot's odometry. Some robots may have GPS, our robot doesn't because it's indoors. Robots may have maps. And a lot of this data hasn't been traditionally used in the computer vision community. But suddenly our cell phones have GPS and there are tons of maps online. Suddenly all the images online, a lot of them are labeled with GPS data. And we suddenly have situational awareness for the vast quantity of visual data out there. So this is a great time for sort of robotics, perception, and the rest of the computer vision community to really come together and focus on the same problems, because the sensors have really been spread out over both fields. So there are a number of components to perception, and this is just a few, and sort of a reasonable ordering, although you could definitely consider reordering them. Calibration, data collection, feature extraction and matching, geometric and scene context, evaluation, and then integration to bigger systems. The rest of my section of talk, I'm going to give an overview of projects at Willow Garage in these areas. It's sort of a random assortment, but it fits into this kind of structure to give you a taste of the things that we do. So let's start with calibration. Let me just play this movie. All right, so calibrating sensors, calibrating single camera is bad enough. We need to calibrate all the sensors on a robot. It's the worst task possible. Nobody wants to do it, which is why it's fairly awful and people put it off as long as possible. But calibrating a robot is extremely important. For instance, if you want to do manipulation and you have bad calibration, at best, you're going to drop what you have in your hand. At worst, you're going to really hurt somebody. So it's very important that you have accurate calibration. And one of the great things about having a standard platform and a community is that someone will write the calibration algorithms once, and then everybody else can use them. So right now, there's a standard calibration algorithm for many of the PR2 sensors, and you can see it calibrates itself for near range cameras, which is great. It means we don't have to go around and calibrate our robots. There's also calibration data available, calibration algorithms available for the Kinect. And there are people out there writing calibration algorithms for their own robots. So if you have other robots, you can run their calibration in ROS as well. It's a fantastic thing about having community. Just write things once and then use them. So once you have calibration, you might think of trying to get data. Now, there are obviously a lot of possible different data sets you can have for different kinds of applications. If you want to do object detection, you need objects. If you want to do scene recognition, you need scenes. I'm going to focus on one that's kind of interesting from a personal robotics point of view, and that's getting data of people. So the motivation behind this project was the fact that we wanted to detect and track people in indoor environments. The catch was we wanted to do it from a robot, so our platform was going to move. And we knew people would interact with their environment naturally, so there was going to be a ton of occlusion. And we wanted to do all of this in 3D. So out of that came the moving people, moving platform data set. This data set was collected from multiple sensors, including stereo cameras, and you can see an example of one of the images in the data set on the top right, and you can see it in the color point cloud in the 3D scene at the bottom, as well as data from both lasers. The data from the base laser is that red line you see in the scan, and a number of pieces of data from the tilting laser are the blue scans. And unfortunately, this was collected before the Kinect came out, but you could think about adding that kind of data to this data set, and we welcome new data whenever possible. So we went around and collected this data at 4 different companies' offices, including our We have about 80 people in the data set, and there's about 4 hours of non-continuous data. So it's a fairly sizable chunk of data. And then we went online and had it annotated using Mechanical Turk. I'm sure a lot of you are familiar with Mechanical Turk. It's an online marketplace where you can send out micro tasks to people, and they'll do small things like label your data for you. So we had them do 2 kinds of labels for us. The first one was an accurate polygon around a person, which is the red line you see in the images. And you can also see a black box. That's a tight bounding box around that outline. The second kind of annotation we got them to do, which I think is really interesting, was this green box, which is where they predict the whole person is, including occlusions. Now, obviously, it isn't going to be nearly as accurate or precise as an accurate polygon, but it does show you where they believe the rest of the person is, whether it be the person's legs behind their desk or the person's body behind a door. And out of about 108 total images, we had about a little over a third of them annotated, which is great. So what are some of the issues that come up? I said there were some interesting issues about collecting this kind of data. Well, what you're trying to do is you're trying to collect natural data of people in their environments, but you are intruding on their environment. So the first issue that you come across is privacy. You're entering workplaces and you're taking video of people, and we're still trying to make this into a public data set. So luckily, actually, people were fairly willing to do this. Out of about, well, I guess there were about 80 people in our data set, so that's about 83 people actually in the environments, because about 3 people opted out. A couple of people just closed their office doors, so we wouldn't take video of them, which is fine. And one person opted out after they reviewed the data and said, I want my data taken out of this data set, which is no big deal when you have a fairly sizable data set. But more importantly well, not more importantly, but in addition to privacy, you have this issue that you're taking this 450-pound, a robot's 450 pounds, robot that's about 4.5 feet tall, into someone's environment and trying to get them to act naturally. The robot's not subtle. It's actually fairly hard to do. So first of all, there are safety concerns. And because of that, we had someone teleoperating the robot at all times. And what that looks like, well, I'm in the picture doing that. With a joystick, you basically walk behind the robot and drive it around. So while it would be nice to collect autonomous data, that's just not realistic when you're trying to get access to other people's offices. It's not going to happen. So what happens when you collect this kind of data? Well, at the beginning of the day, you have 2 kinds of responses that you don't really want. One response is people pull out their cell phone cameras and start taking pictures of this robot that's in their environment. And it's okay to have a few pieces of data like that, because that's pretty much what happens at a demo, so it's not bad to have some of that data. But you don't want your whole data set full of people taking cell phone pictures. The other reaction is that people start talking to the operator. And this guy in the picture on the top right is actually using hand gestures and speaking and doing things he wouldn't do if the robot was there alone. And this data is meant to be used for a later time when the robot's autonomous in this environment. So it's not ideal either. What you want is this very small sweet spot in the middle of the day when people basically ignore you and the robot. But it's a very short time, because as you hang out a little bit longer, you start to annoy people. Suddenly you have this slightly noisy robot spying on you, and people start to close their doors, and then you're done for the day, and you have to leave. So I think these are going to be issues that come up more and more as we try to collect data in natural environments. People are going to know we're spying on them, and we're going to be intrusive in a way. And trying to figure out how to do that and still collect natural data is something that maybe we can learn from anthropologists or other social scientists who are used to doing this kind of thing. Okay, so once we have data, so the next kind of natural step in our perception pipeline is to collect features. So I'm going to move on to another project called the textured object detector. So the textured object detection is something that's been studied a lot in the computer vision community, and there are actually very good detectors out there. Unfortunately, they're closed source or patented, and that's really, really unfortunate for those of us who want to build on top of them. So there's a project going on at Willow Garage right now, which I hope you saw the poster for at the poster session, by Gary Bradsky, Vincent Rabot, and Ethan Ruley to do an open source textured object detector. Very much built on this premise that you can match features, vote for an object, and then confirm the object's pose by projecting it to 3D. Once you have objects detected, you can think about trying to refine your search or trying to refine your detections by using context or geometric information. So let's consider the face detection problem. There are very good face detectors out there. For instance, the one in OpenCV is excellent, but you can't get around the fact that they still have false positives. But if you know something about your task or your environment, you can really constrain where you expect to find a face. So for instance, if I know the size of face I want to find, of course you do face detection at multiple scales, but let's just pick one. And I know I'm looking for people who are sitting down, then I can immediately eliminate, for instance, all the blue pixels in this picture by saying they're too high or they're too low in the scene. They're not where I expect to find a face. I can also eliminate the red pixels by saying, given their depth in the scene, because I have 3D information, there's no way a face of a realistic size could be there. And interestingly enough, I can also eliminate all the green pixels. Now, the green pixels are places where you don't actually have depth information from stereo. But a really interesting fact is that if I don't have depth information, it's because I didn't have texture. And if I don't have texture, I'll never detect a face. So the truth is, if I don't have stereo information, I probably don't need to look for a face there either. So that leaves only the white pixels as actual places where you could find a face of a particular size. And that's a very, very constrained set and really helps you get rid of false positives and speed up detection. So another way you could look at features and geometries is, I'll play this. Features and geometry is by looking at the visual SLAM problem, or the simultaneous localization and mapping. So this is work done by Hauke Strasdad, who is in the video right now, and Kurt Connelidge. So there's a traditional VSLAM problem of you have a moving camera through an environment, you're trying to match features, and trying to figure out where you went and what your map looks like. So they've done a great job of doing this. It's much more efficient, it's a general framework, and it does useful things like closing loops properly. I can speed up the video a little. Oh, not stop the video. Okay, there we go. You can also, if you happen to have RGB and depth information, like from the Kinect, do your sparse matching and then come up with dense scene models, which is very useful with the environment. So while you're mapping, you can also have these dense scene models. Finally, this is skip, doesn't really listen to me. Okay. Another useful thing you can do is build object models by spinning your objects around a circle, doing feature matching, and getting these dense reconstructions. You can get fairly detailed object models. So when you've gone through the whole process, through calibration, collecting data, finding features, using context, you still need to do evaluation. And that's actually a big deal in robotics, because getting close when you do recognition is not good enough. You need to be right 100% of the time. And there's very few computer vision algorithms that are meant to be right 100% of the time. So there's a new Solutions and Perception Challenge being organized by Willow Garage Gary Bradsky that's going to look at actually solving problems and having those out in the public domain so other people can build upon them and rely upon them. So the first challenge is actually at ICRA this year, and it's going to look at textured objects, detecting them and figuring out their pose with data from the Kinect. If you're interested, there's the wiki page, you can go and take a look. And there'll be future challenges in the future. There'll be future challenges that look at other types of data as algorithms evolve, perhaps person tracking, perhaps other things. And finally, perception is interesting for the sake of perception, but ultimately, if you want to be useful, you need to integrate it into a larger system. And this is still very much an open research question. So Willow Garage is helping to organize a number of workshops on integrating perception into larger systems such as manipulation and figure out how to do that effectively. So I'll just take a minute before I pass this off to Radu, because I would be remiss in not talking about OpenCV for a minute at a computer vision conference. The Open Computer Vision library has a huge number of algorithms. It was started long before Willow Garage came around, but is now mostly sponsored at Willow Garage, but is a community development. So some of the new things in OpenCV include full support for Android, which is great, an ever-growing GPU port, has direct Kinect support, a full Python interface, new 2D features, calibration patterns, and fast approximate nearest neighbors. And very soon, you can hope to see actually a lot of the things I've talked about here today integrated into OpenCV, including textured object detection, and a lot of things that take us out of the 2D realm into 3D object capture and 6-degree of freedom poses. And finally, hopefully there'll be a perception app store so we can work around a lot of the issues that have stood in the way of actually licensing out computer vision algorithms for use. And now I'll pass it over to Radu.
Thank you, Caroline. Okay, so we're doing a bit of a good cop, bad cop, white background, black background thingy here. I actually wanted to pick a little bit more on the 2D computer vision community, but Caroline has advised me not to do that. So, hi, my name is Radu. Thank you for being here. What I'm going to talk about today is a little bit of what we call ND perception, and I'll start with explaining what ND actually means. So at the very least, n equals 3. So we come from a geometric background here, where we have scenes with point clouds, right? Point clouds are natural representations for describing collections of points which are 3-dimensional at least. Now, naturally, if you extend this to you add RGB or normal information and so on, basically, your space becomes ND easily. And here's an example. This is a point cloud acquired using a Kinect sensor at Willow Garage. You see a PR2 there. As you rotate around, basically you get much more than just the geometry. You also get a texture attached to the scene. And it's actually very easy to switch between the two. So it's easy to get the image from the point cloud back. So in our opinion, and Caroline I think said this already, 3D has arrived. I mean, I don't know what we're waiting for more. Microsoft came up with this great sensor made originally by PrimeSense. Now they're doing, there are other things probably working on Kinect 2 as far as we know. There's also 3D pocket cameras which are coming out, and I want to mention this because they have a high resolution. So if there's anyone out there actually interested in doing like high quality stereo reconstruction, here's your chance, right? Everybody's gonna have these cameras within a few months or a few years. So there's a real potential for good close range 3D from these devices. Sensors like the Kinect actually are very helpful in robotics, and they enable not only, let's say more expensive projects such as a PR2, but also cheaper robotics. So here you see an example of a Roomba with a Kinect on top, and then there's a quadrotor here from UC Berkeley, which actually I'm gonna show a video of it later. The nice thing is that being cheap and lightweight, it's very easy for people to actually start working on 3D problems, because robotics actually needs 3D. You can't do 2D robotics; it just doesn't work. So, as I've said, I'm going to talk a little bit about the point cloud library, which is one of our efforts at Willow Garage. And as you will see, it's not only a Willow Garage project. It actually started at Willow, but it very, very rapidly spread out across the globe, actually. And you have to think about PCL as OpenCV's 3D sister for now. Just bear with me. So as I've said, we really like Google Maps, so you're going to see that they're all over our presentations. We actually have core developers from over 15, I would say like 16, I think, starting last week, institutions. So it's not, as I've said, it's not a Willow Garage product. We have universities in Europe contributing. There's universities in Japan and universities in the US. Basically, what we're trying to do is kind of focus our attention from. So this is kind of how we see the picture right now, at least at Willow, or how we saw the picture, right? We have this huge field called robotics. There's personal robotics in it, and we're interested in that. And then we have industrial robotics and other types of robotics that we're not going to tackle too much because we have limited resources. And in this field of personal robotics, we have things like navigation, manipulation, and perception, right? And perception is also split again into 2D and 3D, right? And so we really want to shift from this mentality to something like this, where we think they're equally important, and we think that there's a lot of work being done out there in, not only fields like computer graphics, but also other fields, and we can bring that knowledge into robotics, right? So we think that the complexity of, n-dimensional perception, if you want, and personal robotics are equally high. And there's many things that we don't think of on a natural basis. So if we could leverage the broader 3D perception community, I think we could easily advance our specific goals in personal robotics. This is an interesting slide. This is one of our projections actually for the next few years, and this is actually growth. So it's not necessarily the size of the library or anything like that, but because of the Kinect, so suddenly we have a sensor that's available to millions and millions of people, and sure, from that number, a small percentage will actually connect it to the PC. But when they do, they're going to need something like this. They're going to need something that takes the data and does something useful with it, and that's how we anticipate the growth of this project. And Caroline already said this in her talk. Gary and I actually joke all the time about when do we actually merge OpenCV and PCL together, and I think that's going to happen soon. We just have to iterate a little bit over the APIs and see exactly what's the right way to, get ND structures in and not just two-dimensional structures. So to be a bit specific on PCL, for those interested, it is a C++ templated library, completely open source, as you might have seen earlier, BSD licensed as basically everything that we do. Thank you. We're using SSE for optimizations and OpenMP and TBB for multi-core parallelization. And there's actually ongoing work. I didn't want to talk too much about it, but we do have a project starting with NVIDIA soon on actually parallelizing it on GPUs. So we really want to tackle GPUs and clusters of GPUs to solve these problems faster, because in some sense we are overusing x86 for some problems. And our methods are embarrassingly parallel, I think. PCL is split into a variety of tinier libraries. So if you're only interested in 3D feature estimation, you only need to get that library in theory. Same for surface reconstruction. There's a lot of code in there, segmentation, registration, and so on. Basically, if you're interested in these aspects, I can talk to you about afterwards. One of the concepts that we brought with PCL, so coming from a robotics perspective, we realized that there's a lot of roboticists that are not perception folks, and they want to solve problems, but we can't teach everyone, about RANSAC and about feature detectors. So my colleagues that do motion planning, they just want building blocks that they could use. So we thought about a way of basically building modules that are self-sustainable, and we have open interfaces between them, such as for segmentation, you only need to worry about some things, feature estimation, other things, and then put them together in these processing graphs and have our colleagues test them out. So as it turns out, that actually worked really well. We came up with this nice dynamic loadable plugin architecture that our colleagues are using every day. And whenever you see videos with, ROS and perception, you will think about these processing graphs that go under the hood. And the reason why we actually created this is that we noticed that we had a lot of projects that were dealing with, planar segmentation for one reason or another, and we saw our colleagues basically copy pasting the same bits of code all over again in different packages. And what happened in the end is that once we were figuring out what a bug is, or we're trying to fix the original code, those changes were not getting propagated. So obviously we had to build something that would help them more. And in terms of we have a good API, we think we have a good API actually. And doing this carefully with some great software engineers in house, we actually simplify development and testing, I think, quite a lot. Some statistics here. We're only dependent on 3 other libraries: Eigen for matrix computations, CMIMPACT for Levenberg-Marquardt optimizations, and FLAN. Caroline mentioned this earlier, which is a library from David Lowe on fast approximate nearest neighbors. And just roughly, the library is still, we consider it young because it's only been out there for 1 year now. but the code, the bits that we had there were out there for a long time. So just a few examples, a few code examples, because I don't want to really go into the math. I think that's going to bore a lot of people, but just to show you how easy it is to use it. So here's an example of a pass-through filter. All this does is basically takes data and then basically cuts it on a certain with a certain field, a certain dimension, and some limits. You can do downsampling, which is also very important in 3D because a lot of times, again, like we're overusing x86, we have huge amounts of data, and if you're trying to move towards real-time processing, you might need to downsample your cloud. Also, for certain applications, like for instance finding a plane, you don't really need a high density of points. You can just go with a lower density. There's a lot of outliers in 3D data because 3D sensing is still not as good as 2D sensing per se. So you might need methods to remove outliers from the data. And here's an example with a statistical outlier removal filter, as we call it. The classical moving least squares problem from computer graphics applied to real data sets in robotics, again, for smoothing data and again, like cleaning out layers. Very easy to use. You don't have to be a computer graphics expert to use this. Feature estimation is also very important. It's an important topic, not only for registration, but also for surface learning and whatnot. And here's examples of doing normal estimation. You can find curvatures in a cloud. You can find boundary points, which could be of interest for your application. Or as we call them, principal curvatures. So you get like tiny coordinate systems at each point, which again could help you depending on what you're working on. There's classification examples with, here's an example of a fast point feature histogram classification. So you basically train data for surfaces, convex and concave and whatnot. And this is what a simple classifier can give you out. This is something newer called a viewpoint feature histogram, where you look at partial views of objects, and then given the fact that you already have them in a database, like as CAD models, you can recreate some views by doing virtual ray tracing, and then you compare the objects in a histogram space, and the results are really, really impressive. The only prior here is that there's some segmentation existing there, so it's not going to work in high clutter. There's other things like, I'm not going to have time to show everything here, but 2D/3D features, we can call them as 2D because they're in range images, but they're actually in 3D, and these are very useful for segmentation and for registration. And speaking about registration, here's an example. Caroline showed this earlier. In fact, VSLAM is not going to give you the perfect model that you're actually looking for in applications such as grasping, so you need to do a refinement. And here's an example of running a simple, well, I call it simple. It's a classical ICP with some bells and whistles on top that gives you like these nicer models. And again, another example for a larger scene. You're just basically moving your camera around and creating these like nice 3D panoramas. But here using only 3D information. So you can turn the lights off and it's the work. More on segmentation, getting planes out, computing holes out of them, getting the objects supported by them, so polygonal prisms and so on, clustering, segmenting differences between them. There's really a lot of functions there. I'm not going to have time, unfortunately, to show you some. Well, maybe I can show you one example. Maybe I can pick one. Let's see. This is part of what we call the ROS 3D contest at Willow Garage. So we basically encourage people out there to try our software, try PCL, try the Kinect drivers that we wrote, and so on, and come up with cool applications. And we had some prizes behind them. So there were like a lot of students, but also like just engineers all around the world. And we're really like, dazzled by their creativity. I'm not really sure exactly which one is the best to show because I have a few here. This is actually the one that won. So it doesn't have a lot to do with robotics, but we thought that the idea is just like so simple and so, I think innovative in some sense. This is one of our PCL developers, Garrett Gallagher from MIT. And I'm going to skip through it a little bit. But basically what he does is he just draws things on a surface and does like some simple segmentation and then creates like his own virtual whatever piano. It's a really simple stuff. Again, like, it has nothing to do with robotics. But the fact that he did it so fast and he documented properly and released the code in BSD open source form, that was just really something that we liked about. And like more complex things, again, doing visual SLAM. Again, just using 3D data here, not using 2D. So we think there's some advantages to this as well. And finally, I was about to talk more about the UC Berkeley one, but so our colleagues from UC Berkeley, they basically got a quad with a Kinect on top, and they're doing some really, so they're using PCL for segmentation, for real-time obstacle avoidance and segmentation of certain areas. And it's really impressive that, we managed to port PCL to Android, to, it works in Windows, Linux, and on Macs. And it's just great to see people use it for applications that we never thought of. And there's other examples too, but unfortunately, I think I ran out of time. Thank you for your time, and I'll be happy to answer questions.
Thank you. And we have 5 minutes for questions. We're running about 5 minutes late, but that's more my fault than theirs. And you've got that one too, if you want. And please repeat the question.
Well, I have this one here. So.
Are the standard representations for reducing the, like compressing the 3D point clouds or something more parsimonious? I mean, you talked about compressing planar surfaces, but what about non-rigid objects?
That's a fantastic question. We actually have an ongoing project right now. I didn't have time to talk about it. It's a project on point cloud compression. It's really interesting. It's both spatial and temporal. So we're basically looking at so the Kinect is actually overwhelming us with data. We have 30 frames per second, 640 by 480. Our USB bus just goes like, right, CPU spikes and so on. So we want to see whether we can actually do something to reduce the data. So if you're not moving, right, if your scene is static, or even if it's not, what is it from that scene that you're trying to actually investigate? Should you try to do every frame or just, every keyframe? I can talk to you about it afterwards if you're interested.
So the active IR sensors that project the patterns into the scene, you have multiple robots running around, you effectively lose the usefulness of that sensor.
So the sensor on the robot is actually an LED projector. Oh, sorry. The question was whether the IR texture projectors are a problem when you've got multiple robots running around a scene. So the projector on the robot is actually, it's visible light, it's LED, and you can see the texture being projected onto the scene. And it's really only meant to work about a meter away from the robot for like tabletop manipulation kind of stuff. So you're unlikely to have multiple robots really interfering in that space. Now, on the other hand, the Kinect, which is IR basically, if you have a lot of them, they do start to interfere a certain amount. Exactly how much they interfere, I'm not sure, but they definitely do interfere.
So we did do some tests. Well, I don't think they're official, right? But you can get up to 4 or something, and there's absolutely no problem, which is pretty impressive, actually.
Sure. Do you think there's any relevance of the talk this morning, or in general, the 2D community problems that you're solving?
Personally, me or Caroline? she's 2D, and
You didn't want to say anything negative, but go. No.
I can show you the slides that I want. No, I'm kidding. Well, I do think that a lot of 2D, classical computer vision researchers have been stuck in a local minima to some extent, and it's very hard to pull them out of it. There's, as Caroline actually mentioned, there's a lot of sensing modalities that could help us tremendously in robotics, and a lot of people are just plain refusing to use those things. And I think because of that, we're actually progressing slower than we would like to. So there's definitely something to be said about that.
All right, let's thank our speakers again.
Thank you.